Welcome, everybody. Today's speaker is Andrea Lincoln. She's a postdoc at UC Berkeley, and she's going to be telling us about new techniques for proving fine-grained average case hardness. So welcome, Andrea, and take it away.
Great. Yeah. So like Isaac said, I'm Andrea. This is some joint work with Nina and Virginia. And today, the goal of this talk and the goal of the relevant paper is to give reductions from some of our favorite problems in fine-grained complexity to various problems that are hard on average, and use the hardness in the worst case to show average case hardness. And what we'd like to do is give explicit distributions, hopefully explicit distributions that are easy to sample, over which we believe these problems are hard. And I'm going to sort of tell a story today through the prior work up to our work of how you go from this paper Ball et al. In 2017 to Boandasara in 2019 to our paper. So the highlighted results of our results that you can sort of look forward to are a framework where we show how you can give average case hardness for various problems as long as they have something we call a good low degree polynomial. We also introduce a new type of problem. We call it a factored problem, where the factored problem is more expressive than its non-factored associated instance. And we show that the sort of counting version of these various factored problems are hard on average using this framework. We additionally, as an example of the kind of result you can get from a combination of this framework and these factored problems is that counting the number of matches of regular expressions is NM hard on average, which is tight with the algorithmic side. And we can give an explicit distribution for this problem. So I'm going to tell this story about going from Ball et al. To Boandasara et al. Through the medium of clique and how we can do this for various clique problems. But before we do that, I'm going to quickly talk about fine-grained complexity and some of our favorite problems there so that we can sort of motivate why we're using these techniques. So what are some of our favorite problems in fine-grained complexity? And ideally, the thing we want to do, spoilers, we won't be able to do exactly this, but ideally we'd like to show hardness for our favorite problems in fine-grained complexity from their worst case hardness. So a couple of the favorite problems here are KSAT, where you're given a Boolean formula in conjunctive normal form. So it's an and of a bunch of or clauses where the K here refers to the fact that we're oring over K variables. And we want to return true if there's an assignment that satisfies this formula and false otherwise. And Seth is the assumption that KSAT requires 2 to the n times 1 minus little o of 1 time, where this little o of 1 is signifying that this is shrinking as, in this case, K grows. The three-sum problem, you're given a list of n numbers.
What is K, the KSAT problem?
K is the size of the clauses. So we have something that's an and of a bunch of clauses where we're oring K variables together.
Okay, sorry, two-sat is for, yeah, I know what two-sat is.
Right. Yeah, so exactly, it's just the generalization of that. And basically the fastest algorithms we actually have for SAT run in 2 to the n times 1 minus some constant over K. So it shrinks with K, and this is not assuming that those are the best algorithms, but assuming that something like that shrinks in K is the best you can do. Right, so the three-sum problem, you're given a list of n numbers, and you want to find 3 of those numbers that sum to 0. And the three-sum hypothesis is that this requires n squared minus the low of 1 time. Once again, the low of 1 meaning you're shrinking in terms of n. The all-pair shortest paths problem, you're given n nodes and weighted edges, and we want to give the shortest path between all pairs of these nodes. And this is believed to take n cubed minus the low of 1 time. So throughout this talk, I'm going to be throwing these little O of 1s up, and really what it's doing is suppressing anything that's like sub-polynomial, or in the case of these exponentials, sub-exponential. It's sort of suppressing anything that's not a constant in the exponent. What we're really caring about is what the constant in the exponent is, these various problems. So from those sort of core problems, those are the problems and the hypotheses that fine-grained complexity is sort of centered around. There's a couple other problems that are built off of those that have hardness from those problems. So one is the orthogonal vectors problem. You're given a list of n vectors, and I want you to tell me if there's two of those vectors that dot product to 0. And the hypothesis is that this requires n squared minus the low of 1 time. And the super fun fact is that this is implied by Seth. So we can just sort of use the OV hypothesis and then say that, you know, if something is true, is implied by the OV hypothesis, then it's also implied by Seth. Finally, this is the last one, I promise. We've got the zero k-clique problem. You're given a dense graph with weighted edges, and you should return true if there's a k-clique whose edges sum to 0. And the hypothesis is that this requires n to the k minus the low of 1 time. And the fun fact here is in the case of k equals 3, so the 0 3-clique hypothesis, the 0 3-clique problem, this is like looking for triangles. It's implied by both the threesome and all pair shortest paths hypotheses. So we're going to be working primarily with 0 3-clique and OV in this talk. And I'd like to just quickly note that both of these are assumptions that state that these problems just take brute force time. And yet, like, they're implied by a variety of hypotheses that are relatively long-standing and well-believed. Does all of this make sense?
Great. Just one question. Sorry, does the ZKC problem, is that implied by any other hypothesis, or is it independent for k bigger than 3?
Oh, for k bigger than 3, it's independent. Like there are, so there's things like the negative k-clique hypothesis, which implies the 0 k-clique hypothesis, but it's not implied by any of our favorite assumptions, at least that we know of.
I see, thanks.
Yeah, absolutely.
So tell me again what OV is.
Right, the orthogonal vectors problem, you're given a list of n vectors. You can think of these vectors as being roughly log n in length. They're a little bit larger. And I just want you to tell me if there's two of these that dot product to 0. These vectors, we can even limit ourselves to the case where the vectors are 0, 1 vectors. And this problem is still hard from Seth. As sort of the standard setting that people use for reductions because it's easier if it's just 0, 1.
Can you also flash the ZKC hypothesis just for a second?
Yeah. Oh, 0 k-clique, sorry. I was just wandering off into Seth.
Oh, okay. Okay. Thank you.
Yeah, for sure. Great. So we have all these worst case problems, and I covered a little bit of the like sort of web of reductions that exist in this space. But there's been a lot of work in a sort of worst case setting. But there's various reasons to care about the average case, including cryptography. Maybe you're trying to get some lower bound for some learning problem. Or maybe you just sort of genuinely care about some average case distribution for some principled reason. And there's this previous work, Ball et al. 17, and you can think of the goal of that paper as being like, how do we take some of these problems that we know and love and show hardness for some worst, like average case problem? And they totally succeed. They're able to go from worst case OV, for example, or worst case 0 k-clique, and show hardness for this problem that we can call like FOV or F0 k-clique. And what are these problems? They're computing polynomials over finite fields. And the problem of computing them on average is the problem where you're given random entries for all n inputs of this FOV polynomial or F0 k-clique polynomial. So, what kind of properties these polynomials have, what's going on with them? Well, let's say we have some problem P, like OV, for example. We want to generate a polynomial like FOV. We want to do it over a finite field. So Z sub, little p here, some prime, such that it doesn't have too large degree. And you can use this polynomial to compute the answer to your original problem. So in the case of the FOV polynomial and F0 K-clique polynomial they came up with, it turns out that this FP, this OV, for example, computes exactly counting OV. So if you plug in, if you treat this input I as an n-bit vector, that's just the input to your original OV problem, you can use their FOV of I to compute, on any 0, 1 input, the corresponding counting OV problem. So this is the kind of polynomial that they generate. And what they're able to show is if you're drawing a different kind of input, an I hat, instead of from 0, 1 to the n, it's being drawn from this finite field, like every element IID, then computing FP, or in our specific case, FOV, over this random input with significantly high probability in some given time implies an algorithm in that time for our original problem. So this is like a generic framework that they generate where you can, if you produce a problem and an associated polynomial, you can use any hardness for that problem to imply hardness for this polynomial. And so this is where we're getting the average case, right? Like these I hat instances look random. And there's a couple of nice things they're able to do from this. Notably, they have a later work in which they're able to have these useful proofs of work where they can, prove that somebody's actually solved a hard instance of the orthogonal vectors problem or the 0 K-clique problem using this framework that they built. So what's the problem? Well, the problem is while these polynomials exactly correspond to the original problems in the 0, 1 case, it's no longer meaningful. It's not clear how you use counting OV, for example, an average case counting OV instance to solve this factored OV polynomial, this f of OV polynomial. And that's sort of because it's not meaningfully clear what it means to have a single bit in your input be instead an element over this finite field. So they're still able to do really cool things here, but the fact that these polynomials exactly match up suggests that if we could just get back to 0, 1, we'd be able to do something cool. So how do you get back to 0, 1? And we're going to use K-clique as the example to work through because there's this really nice line of work that does so. So Ball et al. Come up with this technique where you can go from, for example, counting K-clique to some average case polynomial over clique. Goldreich, Rothblum sort of actually generate this polynomial and do a bit of work with it. And then Ball and Dessart et al. Come up with this really nice technique that generalizes. And we're going to build a framework from that. So first, let's go through some of this line of previous work. So first, what is this polynomial for K-clique? Well, what we're going to do is have a sum over every possible choice of one, of K different vertices in the original graph. And then we're going to multiply the corresponding edges that correspond to the inside of that clique. So our input here is the n squared bits that correspond to what edges exist in this graph. So once you do this multiplication, I now note that anytime I have K nodes that correspond to a clique, we get a 1 in our sum. And so in fact, we're returning exactly the count of the number of K cliques. So this is nice. We have, a polynomial that has an exact correspondence to the original problem, as long as we have a 0, 1 input. And by the way, this desire for a simultaneously low degree polynomial and one that sort of corresponds in a meaningful way to an original problem is why counting keeps showing up. I'll discuss this later if we have a bit of time, but it would be really nice to get hardness for an average case detection problem. But a lot of these techniques sort of don't really require counting problems. Like it's a problem, if you had a polynomial that gave a detection answer, that'd be fine. But for various reasons, it's sort of easiest to get low degree polynomials for counting problems. Okay, so we're getting these, counting, we have this counting clique polynomial. And when we do the average case, basically you can think of all these edges, instead of being, either a 0 for non-existing or a 1 for existing, they're now some uniformly random entry between 0 and log n. And you can think of this as a multi-edge problem if you like. So, I'm giving you a random graph where I put a random number of edges between 0 and log n on each side, and I want you to tell me how many cliques there are, where if I have like 3 edges and then 1, 1, 2, 1 edges, so the multiplication is easy for me, you then get 6 cliques, right? So you're multiplying the value out on all these edges. So from here, what Goldberg-Rothblum do is they have this sort of gadgety reduction to go back from this multi-edge problem to a problem where you just have cliques. This doesn't give, hardness over the uniform case, but it does show that, counting k-cliques over this particular distribution is hard from the worst case. Ball and al, however, are able to show hardness for Erdős-Rényi graphs. So the case where every single edge is picked with probability 1/2, as an example. They actually show it for various probabilities q that you could pick, but we'll stick with 1/2 today. So if you're picking these random entries in this graph, it's still the case that counting k-cliques there is hard from the worst case. Additionally, and crucially for us, it doesn't sort of look gadgety. It'll sort of look like in the end it doesn't depend on clique, and we can use that elsewhere. So how do they do it? Well, they have all these, cliques. We're going to go down to the k=3 case of clique to make all our examples easy. So they've got all these cliques. Here is one that has, 3 multi-edges on one side, 2 on the other, and 1 on the last edge. To get back to the 0, 1 case, what they fundamentally do is they look at each bitwise multiplication. So notably, the problem of multiplying 3 times 2 times 1 is equivalent to the problem of multiplying all the higher order bits and weighting that by 8. And now we have 3 different problems of each choice of 2 higher order bits and 1 lower order bit multiplied by 4. Every, all 3 choices of 2 lower order bits and 1 higher order bit weighted by 2, and the choice of all lower order bits weighted by 1. And, as is correct, if you, only count things that actually look like cliques and you weight them appropriately, you in fact get out the same sum. So how do you sort of use this to generate a bunch of Erdős-Rényi graphs? Well, let's say we're gonna, have a k-partite setting. So here a 3-partite setting. And so now we're going to pick, our polynomial is going to pick a single vertex from each partition and then multiply the corresponding edges. And now we have this nice property that we know we're going to have exactly 1 edge from A, exactly 1 edge from B, and exactly 1 edge from C. And what we can do is create various instances where we're selecting the ith bit of all the weights in A, the jth bit of all the weights in B, and the kth bit of all the weights in C. And now this looks like a 0, 1 input, right? And if it returns the number of cliques in this setting, the contribution it has to this f-clique polynomial should be weighted by 2 to the j, 2 to the I plus j plus k. So we get out this, sum, we weight it appropriately, and now we, sum over the contributions of all possible choices of I, j, and k. Now you might be thinking, wait, Andrea, are these bits really IID 0, 1, right? Like, you just said that these are random numbers between 0 and log n, or 0 and some prime that's close to log n. And the answer is not natively, but with a little bit of work, yes. So Juan de Sara et al. Have this technique where they sort of take a given number that's equal to like, I don't know, C mod P, and they generate a sort of random, much larger number that has the same value mod P. And now we can use the same technique as before, but all the bits in this big number are very close to random. They have a very small total variation distance. If you're interested in that technique, I can talk about it offline, or you can look at the paper. But the fundamental takeaway I want to have from here is that it got back to 0, 1, and it wasn't really about clique. A final note I want to have is that while in this example, we had sort of degree 3 polynomial and structures and numbers of length 2, and we had to generate 2 to the 3 instances, the generic answer is that if I have b bits and a polynomial of degree d, we need b to the d instances that we're generating. So that's going to be our overhead. All right, so I'm claiming this wasn't really about clique. What was it about? Well, we used the fact that f was the sum of monomials, which were all of degree exactly d, and that it was d-partite in the sense, we're not going to be talking about graphs in general. But what I want is that I can split the original variables that are going into my function into d groups, such that every single monomial has exactly one variable from each of these groups. Additionally, we need that d is, oh, yes?
Sorry, I have a question.
Absolutely.
Was the clique graph d-partite? Like you said it was an Erdős-Rényi graph originally, or that the multi-clique, like, do we change our input problem here, or what's going on?
Yeah, you're totally right. I sort of elided over this. So what they use to go from worst case to average case is the thing you can immediately show to be hard in the average case is that sort of k-partite Erdős-Rényi graphs are hard, but you can use that plus a couple of calls to an Erdős-Rényi like solver using inclusion-exclusion to deal with the fact that in a normal Erdős-Rényi graph, there are edges inside, the partition, inside one of these partitions. I don't know if this pointer will work. But if there are edges within this partition, sure, we don't want to count those cliques, but we can just make a bunch of calls to, for example, the sort of just the B portion of the edges and vertices, just the C portion of the edges and vertices, just the A portion of the edges and vertices, then the A and B portions, the B and C portions, the A and C portions, and using inclusion exclusion, you can remove those edges. But yeah, you're totally right. I just like elided over the difference between a k-partite and not k-partite version. But yeah, so that's exactly what they do. They have a technique to get around that.
All right, cool.
So in addition to this sort of d-partiteness that we're abusing to make our multiplications work nicely, we need that this degree of our polynomial is not too big. And this is because our overhead is exponential in the degree of our polynomial. Sorry, getting a little warm. Finally, something we sort of used was that the output of whatever this function f is and our problem p need to be exactly the same on 0, 1 inputs. And the reason we need this is that we need it to be the case that we can solve our problem p from using f on average. And then once we have this average case instance of f, which we like take back to 0, 1 instance of f, we need to use our problem p to solve that 0, 1 instance of f. This condition that they be exactly equal is stronger than we need. Like you would just have reductions in sort of every step that I described. But in order to like make this framework simplest, we just insist that they be equal on all 0, 1 inputs. And also, as it turns out, a lot of the polynomials that are generated and we care about are exactly equal, at least for these counting problems. So what does this look like more formally? We define this notion of strongly d-partite, which is basically what I described before. Every every monomial is of degree D, and it has exactly one entry from each of our partitions. The kind of degree we need to look for is something that's little o of log n over log n. That allows our total overhead to be subpolynomial. And we ask that the output of this function and the output of the problem on 0 and inputs are exactly equal. So what do we get from this? If a problem P has a good low degree polynomial and it requires an amount of time in the worst case, then you can say that the average, the uniform average case of that problem better require, T of n to the log n to, times log n to the D time, where this is going to be subpolynomial if D is small enough, as long as that algorithm to solve this problem succeeds with sufficiently high probability, where here that probability is going to be 1 minus 1 over log n to the D. So we can reframe this sort of not worrying about exactly what our degree D is by saying, anything that's subpolynomial, and if you, claim to succeed with a probability that's larger than any subpolynomial, then you have to take the same amount of time. So this is the worst case to average case reduction, and this is where our overhead is coming. And the reason for this overhead is because we're generating all these different instances and we need correct answers on all of them. So great. I'm going to do my best to always mention the probability throughout the talk, but if I ever slip up and I'm talking about the average case, like this is the probability that is being described the rest of the talk because we're using this framework. So great, this wasn't really about clique. If we have a good low degree polynomial for a given problem, we can go from the worst case instance of that problem to the average case of this, an average case instance of this good low degree polynomial being hard, back to the uniform average case of that problem being hard. But the uniform average case here is every single bit I is chosen to be 0 or 1 with probability a half. So what can we do? Our first hope might be like, hey, let's show that orthogonal vectors or 0-3 clique are hard on average. Unfortunately, the polynomials we can come up with for them are too high degree. And in fact, there's good reason to believe you shouldn't be able to do this for orthogonal vectors. Notably, counting orthogonal vectors on average is actually, you can do it in faster than n squared. You can sort of violate the orthogonal vectors hypothesis on average. So one thing we can do is, instead of looking at cliques, you can look at any subgraph. And once again, like Isaac pointed out, you get this sort of K-partite Erdős-Rényi graph, not a normal Erdős-Rényi graph, but you can use something we call inclusion edge exclusion. Puns. To go back to just a regular Erdős-Rényi graph being hard for counting any arbitrary subgraph. But a key part of what we're going to talk about is what you can see in the upper right-hand corner, factored problems. So what we're going to do is we're going to generate factored versions of orthogonal vectors in 0-3 clique, and we'll be able to show hardness for those on average. And we're sort of ironically going to get lower degree from these more expressive problems. They're going to be harder versions of the originals. So let's talk a bit about factored problems. First, let's remind ourselves what OV is. We're given n vectors, and we want to return true if there's 2 of those vectors that dot product to 0. Here, u and w don't dot product to 0, and u and v don't dot product to 0, but v and w do. So when we go to the factored version, instead of having, some vector of length 6, what we're going to have are vectors that are factored in the sense that they are represented by g different sets, each which contain various b length strings. So here we have 2 sets which contain 3 length strings for each factored vector. And intuitively, each factored vector is representing all of the vectors that can be formed by choosing 1 string from each set. So generically, if we're choosing, g and, and then finally, if we need to represent something that originally had some dimension, then we need g times b to be larger than that dimension or equal to that dimension. So great, we've got all of that. But these sets can be quite large. You know, here they're not. They're, you know, size 4, 6, and 0 respectively. But it turns out you can still compute really quickly out of all the represented vectors in, for example, U and V, you can compute really quickly how many orthogonal vector pairs there are. So we can sort of do the count over these factored vectors quite quickly. And how would we do that? Well, you know, here's all the pairs in the first set of inputs that dot product to 0. And here's all the pairs in the second set of vectors that dot product to 0. And we can simply multiply them. Like the number of vectors that are, you know, concatenations of something in the first set and concatenations of something in the second set that form orthogonal vector pairs between U and V is just going to be the multiplication of those two values. And we can instead, you know, sort of do this out manually where we write out all U vectors and write out all V vectors and then look at all pairs here, but these values are going to be the same. And so conveniently, as long as G and B are not too large, we can do this representation. Just a quick note to give some intuition. You know, with U and W and V and W, we're just going to get 0. And this is because, you know, we have the empty set. We allow the empty set. It's trivial. But these are sort of, you know, set representations of these vectors. Notably, if you want to represent an original OV instance in this setting, you can simply have G sets of B-length strings where each set of B-length strings just has a single vector in it. And this will allow you to represent sort of your original OV instance. So factored OV defines these factored vectors, and then the counting version of factored OV asks for the count over all pairs of vectors in its output. And there are G sets of B-length strings. So, you know, how big is this? If we, you know, can represent vectors of length D, we need G times B to be greater than D. You can sort of think of the length of OV vectors in our sort of normal setting where it's hard as being just a little bit larger than log n. So we could set, you know, B to be root log n and G to be just a little bit larger than root log n, or we could set B to be, you know, log n divided by log n, and then G can be something that's just a little bit larger than log n, as an example. So, you know, how much space does representation take? Well, it takes G times B times 2 to the B space. And basically, as long as 2 to the B is not too large, we're going to have, you know, an efficient representation. And the reason we like want to make G small, that we want to make B as large as possible, is that as it turns out, the polynomials that we can generate for these factored problems have degree K times G, where K is, you know, 2 in the case of OV and 3 in the case of factored 0-3 clique. So we've, you know, been able to reduce the degree of these polynomials significantly. And as a result, we can, you know, represent them as these good low degree polynomials. As a result, these counting factored OV and counting factor 0-3 clique are hard on average in their uniform average case. So what does that uniform average case look like? Well, you have these factored vectors. Here I'm representing, you know, some vector U that has its sets completely filled, you know, 2 sets of these 3-length vectors. When we're generating a uniform average case, for all the possible 2 to the B strings that could exist in each set, we leave it there with probability 1/2. So we're sort of flipping coins to include or not include each possible string. So, you know, these are like concatenations of uniformly random sets of strings. So what do we get? We get that counting factored OV is n squared minus the low of 1 hard from Seth, because OV is hard from Seth, and you can solve OV with factored OV. We get that factor 0-3 clique is n cubed hard from all pair shortest paths in threesome, because it can solve 0-3 clique. Additionally, it's hard from Seth because it turns out that this counting factored 0-3 clique problem can solve orthogonal vector problems, like specifically the 3 orthogonal vector problem. So we can use this extra freedom we get from this factored problem to in fact make this hard from everything. I highlight this because this means that this counting factored 0-3 clique problem is a new candidate hard from everything problem. So, you know, if you've got some problem that's really hard and you can reduce it to counting factored 0-3 clique, you get hardness from all the favorite, you know, assumptions of fine-grained complexity, and you incidentally get a average case distribution for your problem. So what are these factored problems good for anyway? Reductions. The convenient thing we have about them is that these counting factored problems can use a lot of the same techniques that the original problems we're sort of reducing from can use. And why? It's because they sort of look very similar. They have a lot of the same structure and sort of combinatorial vibe to them. You know, yes, we have this like increased representativeness of these sets, but it turns out that a lot of reductions still basically work. I'm going to give a super high-level description of one of our reductions, this counting k node labeled ST connectivity problem. So what is this problem? You're given n nodes and m edges, and your nodes are colored from some set of color C, and edges only exist between nodes of different colors. That final restriction is there just to make sure that there is in fact an efficient algorithm. And finally, you know, with the counting version, we want to count the number of paths from S to T that only use S colors, that only use K colors. And we're counting this mod something reasonable, and that's also to get efficiency because you can generically generate just a huge number of paths. So we need it to be the case that you can count pretty easily. So we're going through and we're counting all these paths. We can get an algorithm that's pretty efficient. This algorithm like looks kind of naive. You just guess the K colors and then check if there's a path in those colors, or in this case, in the case of counting, you count how many paths there are using those K colors. And it turns out we have a matching lower bound. If the factored 0K clique problem is hard, as hard as we believe it is, then counting K node labeled ST connectivity requires as much time as we claim it does. This, you know, number of colors to the K minus 1 times edges time, ignoring subpolynomial factors. So I'm going to give a super high level idea of what this reduction looks like. So we start with factored 0-3 clique, and we have these 3 gadgets, and we have various vertices that appear throughout this. And these vertices are colored in some way that matches like a coloring you make of the nodes in the original problem. And what we're going to do with each gadget is check how many ways there are to match up that factored vector set. So this first gadget, here represented by a rectangle in red, once I've chosen some colors, let's say I choose the dark red, the dark green, and the orange. Once I've chosen those colors of nodes, the number of paths to get through from S to the out port of this gadget is going to be equal to the number of, for example, you know, 0K clique matches in their first set. And, you know, this purple diagram is going to be the number of matches you get in the second set, and the final darker purple is going to be the number of matches you get in that third set. Excuse me. As a result, the number of paths from S to T when you've chosen all these node colors is going to be the multiplication of those values, and thus it's going to be sort of the count of the number of factored vector matches you get on a given set of factored vectors that you've chosen in your input. So we get out exactly what we want. You know, how big is this? Well, each color is representing a node in the original, so our number of colors is n. And each edge, I sort of haven't explained what's going on in the internals of these gadgets, but each edge is basically going to correspond to an edge in the original, like one of the, you know, factored vectors that's sort of written onto an edge value instead of a weight. Given these values, what do we get? So we start with a problem that has n nodes and n squared edges, and it's believed to be n cubed hard. And we end up with a problem that has n colors and n squared edges. And similarly, this reduction works directly, so it should be n cubed hard if factored ZR 3 clique is n cubed hard. And we can rewrite this n cubed as, for example, c cubed plus c times e, right? So we can say that if you can solve this problem significantly faster than c cubed plus c times e, then you're violating the factored ZR 3 clique hypothesis. Great, so this matches our algorithm. We get this tight lower bound. The final thing I'd sort of like to note is, what does this mean for example, this counting factored, this counting node label SC connectivity problem? Well, our counting factor 0 problem is hard and hard on average from 3OV, Seth, APSP, threesome. As a result, this counting 3 node labeled SC connectivity problem is going to be hard from, once again, all of our favorite problems. But we'd like to further note that you can actually get average case hardness here. It's no longer uniform because we're sort of passing it through our gadget, right? But we have some average case distribution for this counting factored problem. And we can pass that distribution through this gadget. And if you can solve over that distribution with good probability, then you can solve the factored 0 clique problem with good probability. Then you can solve 3OV, Seth, AP, you can violate 3OV, Seth, APSP, and threesome if you can do that sufficiently quickly. So any reduction that goes from some problem that's hard on average is going to generate some average case distribution for your problem. And the probability can be lower than before because we're coming from specifically, the threesome, Seth, APSP setting. We don't have a degree that's generically as high as it could be. We actually sort of can use a degree that's lower and have a lower overhead as a result, and thus have a higher probability of success that we can, we can have a lower probability of success that we can stand. I'd like to talk briefly about regular expression matches and then not get into reduction at all. So there's a reduction to regular expression matching in the worst case. And you can take this instead to be an average case hardness for counting regular expression matches coming from counting factor 2OV. So if you're given some regular expression R and a string S, and you want to count the number of ways to match R to S, there's an algorithm that runs in size of R, size of S time to do this counting. And we have a lower bound that comes from this factor 2OV hypothesis and says that that's tight. And factor 2OV is hard from both 2OV and from Seth. So to put this all in a picture, we have these pre-existing problems in blue that are sort of considered central to fine-grained complexity. We've got these reductions that predated us that are in red and have the dotted lines. And then we've got what shows up in this paper, where we generate these problems of average case counting factored problems. And we can get hardness either from all of our favorite fine-grained hypotheses or from at least one of our favorite fine-grained hypotheses, and use that to get hardness for a variety of other graph and string problems. I want to briefly show a bunch of reductions that we didn't cover in this talk but exist in this paper. Both to sort of highlight that it turns out this framework and these factored problems really can be reduced to a variety of different problems. You can say something about LCS, you can say something about edit distance, you can say something about this partition matching triangles problem. These have a lot of ability to be reduced to other problems. I also want to note that the factored problems are in some sense complete. Like factored KOV, you can, instead of talking about whether or not your vectors are orthogonal, you can talk about some other function over your vectors, like how many pairs in each set are equal to each other. And it turns out factored KOV can solve any function. So there's some sense in which these factored problems are complete over the set of factored problems that you could possibly have. And this completeness is in fact sort of how we get that zero k-clique is hard from KOV. So results in this paper, we build this framework based on the sort of ideas and results of this Bois and Desara paper from 2019. We generate a new type of problem, a factored problem, and using a combination of the framework and these factored problems, and then reductions from those, you can show average case hardness for various string problems and graph problems. And notably, you can show average case hardness for this node label SD connectivity problem from factor 0.3 clique, which means that you get that hardness from the any assumption of APSP3 sum or Ceph being true. Suddenly, like this distribution is hard. And as a result, we get a new candidate hard from everything problem. Some things I didn't talk about, or at least didn't talk about very much, are that we show that counting OV is easy on average. So we sort of give an explanation or excuse for why we weren't able to come up with really efficient polynomial for OV, because it would imply something that violates OV and Ceph. We also, as I briefly mentioned, get a reduction from counting to detection for average case 0 k-clique. So the reason this is interesting is you can't do this in the worst case. It appears that counting problems are harder in the worst case. But here, if you believe that counting is hard, you should believe that detection is hard. In the case of vanilla, not factored, 0 k-clique. This is also relevant to some previous work about fine-grained cryptography. And finally, we get average case hardness for counting any small subgraph as opposed to just counting cliques. You can say that, if finding 5 cycles, for example, is hard in the worst case and counting them is hard in the worst case, then counting those 5 cycles is hard on average. Any questions?
Okay, so I had a question.
Yes.
Thanks for the talk. So I guess I'm kind of curious, like you made this comment about how low degree polynomials kind of jive well for these counting problems where you're trying to count things of like constant or small size or something.
Right.
Are there like examples in this space of polynomials or like a problem that somebody considered where it was kind of surprising that there was like a small polynomial to like count the thing that they were interested in, and it wasn't just like summing over all possible like instantiations of the thing?
I can't think of one. Yeah, I think all the polynomials that have been used in this setting are exactly just summing over all possible witnesses and then having some not too high degree way of checking whether or not this witness is valid. There's some polynomial, the vanilla, the sort of Ball 0 k-clique polynomial needs to check whether or not numbers sum to 0 in some way that's low degree. And they're able to do that. So they have something sort of interesting going on there that's non-obvious. As soon as you move to the factored version, you get to sort of like cheat by the fact that it doesn't really matter what your function is, because you're basically just writing down every possible multiplication of choices of strings. Like every string is now represented as like a single variable that's either there or not. And you can just like write out a monomial that's a multiplication of all the valid sets of strings that you can have. So it's pretty straightforward.
Cool, thanks.
I had a question.
Yeah.
So you mentioned for the pathfinding counting problem, you ended up with a non-uniform distribution.
Yeah.
Are there any problems where where you've been able to get a uniform distribution out of this, like for the original problem that somebody maybe cared about before you came along, by this technique?
So I think the only one is where we can apply this technique basically directly. And so only for like counting any small subgraph. So like,
Okay.
which, you know, is maybe not that surprising because that's what Bondasar et al. Were able to do for a clique, right?
Okay. Okay.
Yeah.
But not for like the counting regular expressions or other problems like that. Okay, thanks.
Yeah.
So
Yeah,
sorry.
sorry, go ahead, Danny.
I had a question about what you said about the regular expression match problem. So you said it was R times S, or the length of R, the regular expression times the length of S. That was the best known bound, but can't you do a pre-processing of the regular expression into a finite state machine and then do it in, I guess it's exponential in the size of R, but it's still, but then it's linear in S when you do that, right? So it's 2 to the R plus S, isn't that right?
I would believe that that works. In this case, we treat R and S as like inputs, and the kind of R and kind of S that work for this reduction are going to be both about size n. So
okay.
Like if you had like a specific fixed regular expression, I think what you're saying totally works. And then like sort of you only take S time because you can do this pre-processing. But yeah, as it turns out, like there's sort of a framing of this where like somebody hands you a document and somebody hands you a regular expression and asks you to find matches in that document.
Okay, so I know this is maybe a dumb question, but so all of these problems, basically you set up a whole framework that's kind of like NP completeness where you haven't proven any of them are hard.
Absolutely.
But you just you relate together, you relate them to each other so that if any one of them is proven, or maybe it goes only one way in this case, or I guess there's various cases where you go both ways or one way, and then if a certain algorithm turns out to be like the OV algorithm, then that suddenly you solve all these other problems in a more efficient bound. So it's kind of, yeah. So it's probably a hard problem if it reduces, so many problems are reduced to that. I don't know. Is that philosophically the?
Exactly. Like I think the metaphor to NP hardness is one that's often used in fine-grained complexity. We absolutely use these like conditional lower bounds. For what it's worth, there's like not really that many unconditional lower bounds on computation style things. Like you can get unconditional lower bounds for a lot of information theory style problems you might ask, but if you've read in your entire input and you're now trying to claim that you take significantly longer than the size of that input, you know, we've got the time hierarchy, but basically like for any problem you can think of that's not like part of the time hierarchy theorem proof, like we don't know how to do anything unconditionally. And so exactly just like NP hardness, we're like, okay, like let's just build a giant network of reductions and at least explain why it seems to be hard for us to make these improvements, like has some sort of shared reason. Like the reason that it's hard to solve KOV is sort of coming from the same reason that it's hard to solve SAT faster.
Okay, thank you.
Yeah, Andrea, I recently saw a very nice paper by Oded Goldreich, which said that if you want to count cliques mod 2, then there was a very slick worst case, average case hardness. Have you thought about any of such modular counting problems for your questions?
Yeah, actually, so I also, yeah, I like that paper. So it turns out there, I emailed Oded and Oded told me, and I think it's now represented in his paper, there was a previous version of this that apparently exists in the Bondasar paper, but I'll admit to having also not like seen or noticed it when I read that. And I agree that the Oded version is very slick. It turns out that you can sort of take that technique and apply it to our factored problems, and it just works. So, and by it just works, really what I mean is that in our framework, if you have a good low degree polynomial, you can use that same kind of technique and it works. And there's a couple of nice things. One is you get lower overhead. And the other is now instead of getting counting hardness, you get modular hardness for everything. So we have been taking a bit of a look at that. But yeah, they sort of, they plug and play really nicely as it turns out. There seems to be something like sort of central to why a lot of these techniques work for playing around with these polynomials that has to do with what the degree of that polynomial is, and then also whether or not it like looks like this strongly departite thing. Like if you get this strongly departite setup, then like you're just in business.
So I guess one open question there seemed to be in Oded's work was like improving the error. Like, can you really say it's hard on average even to do slightly better than random guessing? You know, does this factored framework make any of that potentially easier to obtain, such strong average case hardness?
So unfortunately not. We sort of carry through this problem where we ask for exactly correct answers on like something that grows exponentially in degree of our polynomial instances. I do think like we've thought about it a bit. Like the original ball it all technique does not sort of have this problem. Like it's sort of, you know, it's interpreting everything as polynomials are a finite field. And then it's like, okay, great. Like if you're a polynomial of a finite field, I can like ask a bunch of random points as multiplied by like, roughly you take your input and then you add to that x times some random input plus x squared times some other random input. And now you've got like some combined input and it's a very low degree polynomial in terms of x. And then they're like, hey, did you know that there's various techniques for figuring out what the true polynomial is given a bunch of points that like, where only, you know, 2/3 of them are actually on the curve and 1/3 aren't. And then you can like get back to your zero, and your zero is exactly the input you cared about. So they use that technique. And if you can do something similar in this 0-1 case, you'd be golden. But it's not clear to me how to do that. And so you do get lower overhead. Instead of getting log n to the d, you get like 2 to the d in this modulus case. But that's sort of it.
Okay, thanks.
Yeah.
All right, well, seems like that's all the questions. So thank you, Andrea.
Yeah, thank you for having me.